Okay, so we've looked at the quotient in determining power. Now let's look at how we take that energy measurement, which is a product, the kilowatt hour unit of energy, and how we determine what this is really telling us. The joule, J, has been defined as the unit of energy. However, there is another way to express energy. Since power is expressed in watts, and time in seconds, units of energy called the watt second, watt hour, and kilowatt hour can be used. So kilowatt hour ought to be familiar with you. Anybody that's had a power bill and you had to pay for your electricity, you'll notice that on your bill it's a measurement in kilowatt hours. Okay, so that's a product and not a quotient. When you pay your electric bill, you're charged on the basis of the amount of energy you used, not the power. Remember, power is a rate, okay? So because power companies deal in huge amounts of energy, the most practical unit is the kilowatt hour. You use kilowatt hours of energy when you use 1,000 watts of power in an hour. For example, a 100-watt light bulb burning for 10 hours uses 1 kilowatt of energy. Okay, and we can see the mathematical relationship here. Okay, notice again, it's a quotient. Power times time. 100 watts of power times 10 hours gives us 1,000 watt hours, or 1 kilowatt hour. So to determine the number of kilowatt hours for each of the following energy consumptions: 1,400 watts for 1 hour, 2,500 watts for 2 hours, 100,000 watts for 5 hours. So in every case, we're just going to find the product here. So 1,400 watts, 1.4 kilowatts, times 1 hour gives us 1.4 kilowatt hours. 2,500 watts, okay, in 2 hours, 2.5 kilowatts times 2 gives us 5 kilowatt hours. And 100,000 watts for, what did it say, 5 hours. 100,000 watts, 100 kilowatts for 5 hours is 500 kilowatt hours. Okay, so don't get those confused. This is a measure that uses a product, not a quotient. Okay, so anyway, those are the problems we just worked. Go ahead and take a look at them again. Again, pull out your notebook, crank through them, prove it to yourself that it in fact works. How many kilowatt hours are used by a 250 watt bulb burning for 8 hours? Again, just put it in the relationship. 250 watts is 0.25 kilowatts times 8 hours. We get the product 2K watt hours, 2 kilowatt hours. So let's look at heat. We talked about how heat is a factor. The generation of heat, which occurs when electrical energy is converted to heat energy in an electrical circuit, is often an unwanted product of current through resistance in a circuit. Remember, heat is a killer. On any electronics, heat is a killer. It degrades the devices. In some cases, however, the generation of heat is the primary purpose of the circuit, such as an electric resistive heater, your little space heater, your blow dryer for your hair. Anything that uses electricity and current in a resistive nature to create heat that's the intended use. In any case, you most frequently deal with power in electrical and electronic circuits. Okay, so after completing this, we'll take a look at calculating power in a circuit, determining power when we know current and resistance, voltage and current, voltage and resistance. When there is current through resistance, the collisions of electrons produce heat as the result of the conversion of electrical energy. The amount of power dissipated in an electric circuit is dependent upon the amount of resistance and on the amount of current expressed. Typically, the power expressed as the I squared R, we call it I squared R loss. We're talking about energy where we're converting electrical energy to heat energy, I squared R loss. P is the power in watts, I is the current in amps, R is the resistance in ohms. You can get an equivalent expression for power in terms of voltage and current by substituting the voltage for IR. I squared is equal to I times R, or I times I. So if we put it in our expression, I squared R, I times R, we know that I times R then is V. So we end up with a conversion here, and that's all this is showing us, is how we went from I squared R to power equal to voltage times current. We'll take it one more step. Okay, so in this case, we're looking at voltage and current. You can obtain the other equivalent expression by substituting V over R for I. So we use the same terms that we had up here. Power is equal to V over I. Now we're going to substitute V over R for I, and we end up with V squared R. So in your notebook, you should write down these relationships. Power is equal to I squared R, is equal to V times I, is equal to V squared R. Sometimes this relationship, power is equal to V over I, is the same one we say power is equal to I times E, pi, as a quick mnemonic to remembering power is equal to I times E. So if we look at what goes on in a circuit with I squared R loss, current through a resistor, as it heats up, as the electrons start colliding with each other, we end up with heat loss. And this is just showing a radiation of heat produced by current through a resistance as a result of energy conversion. Okay? Power dissipation in an electric circuit results in heat energy given off by the resistance. Sometimes that's a good thing. Sometimes that's not so good. Okay, so we use that I squared R relationship. The generation of heat, which occurs when electrical energy is converted to heat and in an electric circuit, and is often unwanted byproduct of the current through the resistance in a circuit. Thing to remember is there's always some loss. There's always a certain amount of power dissipated in an electric circuit, and it is dependent on the amount of resistance and the amount of current. So you can never get away from that. There's always going to be an amount of I squared R loss or heat. You just want to be aware of it, and if it becomes too excessive, then that becomes a problem. The relationships between power, current, voltage, and resistance then expressed in the preceding formulas then are known as Watt's law. So if you ever get a question about talking about Watt's law, that's everything we have talked about in the last 20 slides. In each case, current must be in amps, volts must be in volts, R must be in ohms. To calculate the power in a resistance, you can use any one of the three power formulas depending on what information you have. For example, assume that you know the values of current and voltage. In this case, you calculate the power with the formula power is equal to V times I, or I times E. If you know I and R, use the formula power is equal to I squared R. If you know V and R, use the relationship power is equal to V squared R. So again, more tools in that tool bag that you have to keep up with and have ready for your analysis on your circuits. Okay, so when we come back, let's do some we'll do some continuation of the relationships.